Uh, so in this video we will talk about the necessary condition for the for iterative solver to converge, and that condition is called diagonal dominance. So we have a matrix that is given as A11, A12 going up to A1n, then A21, A22 going up to A2n, then we have AN1, AN2 going up to ANn. So the diagonal dominance is defined as I is greater than or equal to summation of j going from 1 to n while j is not equal to aij. So this is called diagonal dominance. Now if aii is equal to j is equal to 1 to n, j is not equal to aij, then this is called weak diagonal dominance, and this matrix we will be able to converge via this iterative solvers which we discussed, like Gauss Seidel or Gauss Jacobi method, but it will take more number of iterations to converge this matrix because this has the weak diagonal dominance. Now the point is that this kind of matrix is achieved when we do the steady state solution of the conduction equation that we will understand in detail later. Now this second, if this aij is greater than j going from 1 to n, where j is not equal to aij, and if there is this greater sign, then this is called strong diagonal dominance, and this matrix we will be able to converge very easily. So if there is this greater sign, then the number of iterations required to get the converged solution of matrix system Ax is equal to B via either Gauss Jacobi or Gauss Seidel method will be low. And if we have the equality sign in here, that this aii is equal to so basically the diagonal element is equal to the sum of all the non-diagonal element in a row, then it becomes a weak diagonal dominance case, and in this case we will need more number of iterations to find the solution of Ax is equal to B via iterative solvers like Gauss Seidel and Gauss Jacobi. So that's what diagonal dominance means, and this diagonal dominance is the necessary condition for the iterative solvers to converge. So if we do not have the diagonal dominance, then it is necessary to swipe the rows in such a way that we get the diagonal dominance. So the point is that if we don't have the diagonal dominance, then iterative solvers doesn't converge. So we must do row or column swipe in, or we can say it exchange in such a way that diagonal dominance is. So suppose this is my matrix, like we have this 2 0 1, and then we have this 2 1 and 1. and then so we have this 0 2 1 2 1 1, and then we have this 0 0 2. So no diagonal dominance, but exchange first and second row, then it becomes 2 1 1 0 2 1 0 0 2, and we have the diagonal dominance. So we must make sure before trying to find the solution by a Gauss-Seidel or Gauss-Jacobi method that the matrix is diagonal dominant, and if it is not if it is not diagonally dominant matrix, then we need to do row swipe or column swipe in such a way that we get the diagonal dominance. So in this case, we could have exchanged these columns as well, and if we exchange this, then 2 will come here and this 2 will go here, so this will become the diagonal dominance matrix. So that kind of things we need to make sure. But if we do the column swipe, then we need to make sure that the vector x changes, and if we do the row swipe, then the vector v changes, which we have already talked about in Gauss elimination method when we tried to find out the lower triangular or upper triangular matrix via row operations. So now let us take one example of this Gauss Seidel method. So we have this 2 1 0 1 2 1 0 1 1, and then we have this x1 x2 x3 is equal to 1 2 4. Find solution via Gauss-Seidel. So let us assume that x0 is nothing but 1 2 1 transpose. Then x1 will become x1 at first iteration will be nothing but 1 minus 2 times 1 minus 2 times this will be nothing but 1 minus 2 times 2 this will be if we apply the Gauss-Seidel, then this will become x1 at first iteration will be nothing but 1 minus 1 into 2 minus 0 into 1 upon 2, and x2 at the first iteration will be nothing but 2 minus 1 into x1 1 minus 1 into 1 upon 2, and then x3 1 will be nothing but 4 minus 0 times x1 1 minus 1 times x2 1 upon 1. So these are the values of the vector x1 will be nothing but x1 1 x2 1 x3 1 transpose. Similarly we will have x2 the value at the second iteration, and it will be nothing but x1 at 2 x2 at 2 and x3 at 2 transpose. So this is how we will calculate, and finally we will see that the solution is x vector is 3 minus 5 9 transpose. So this basically satisfies all the equations. So if we put it into the first equation, then it is nothing but 3 to the 6, and 1 minus 6 is equal to 1 minus basically this is nothing but 1. If we put it into this, then it becomes 1, and then 3 3 3 minus 10 plus 9, and then this gives me 2, and 0 minus 5 plus 9, and this gives me 4. So this is the final solution that will come out of this. So thank you so much, and this is where we finish the iterative methods or indirect methods of matrix solution. Thank you.